And so this is our what is usually the Simondon study group, but today we're continuing our reading of Cavailles and Lotman's text, Mathematical Thought, that we started last week. So last time we read through Cavailles' section, his part of the presentation, and so we saw his version of what the dialectic means in relation to mathematics. And for him, it has to do with this intertwining of necessity and contingency in the evolution of mathematics. So in relation to a particular problem, there's always a certain contingency from when you're looking at the problem before it's solved. So you have a contingency in terms of how the problem will be solved. There's no way of sort of reading off the solution of the problem from the statement of the problem itself, and so it requires creativity and some sort of novelty to actually solve a problem. But then on the other hand, after the problem is solved, you have this form of necessity. So you can look at the problem after it was solved and say, yes, of course, this is the new concept or the new technique or whatever that was needed to solve this problem. And you can sort of retroactively say that there's a necessity to this solution. And so this dialectic has to do with holding on to both the necessity and the contingency at the same time, and not sort of taking one as real and the other as not real, or something along those lines. So we have to hold on to both and sort of constantly remind ourselves of each side, even though from one angle the necessity might seem more obvious, or from another angle the contingency might seem more obvious. But we have to sort of keep the other one in mind in each of those situations. So that's sort of the positive side of what Cavailles presented, and there was also the negative side where he argues that certain conceptions of mathematics that were proposed in the late 19th to early 20th century, namely logicism and formalism, these conceptions of mathematics are no longer viable because of certain technical results in logic, in particular Gödel's incompleteness theorems. They have the result of making some of these conceptions not viable. And likewise, in the case of logicism, there's the fact that the various consistency proofs that have been, or the various systems of attempts to derive mathematics from logic have all had to appeal to non-logical principles. So the principle of complete recursion, for example, you have to use these principles that are can't really be described as logical. You have to use them in your construction at certain points. And so the idea that mathematics would be reducible to logic ends up not working for these attempts. And then the last thing that we ended on, and that we didn't have a chance to go into in any detail, was that Cavailles alludes to the what's called the Skolem paradox, and he gives a very brief statement of this paradox. So he says, this is on page 7 of the PDF. He says, if we have a model which we assume satisfies a system of axioms, it is always possible to construct a countable model satisfying that same system of axioms. In particular, one can satisfy the system of axioms of set theory with a countable model. He just states this very briefly, and he as he says earlier, he can't go into the details because he would have to actually establish a certain formalism and then prove this result within that formalism. But the Skolem paradox has to do in particular with a first order model, a model of first order set theory. In set theory, you can prove that not all infinite numbers are the same in size, essentially. So in particular, there's a difference between countable infinities, like the set of natural numbers, 0, 1, 2, 3, etc., the countable sets are distinct in size from various uncountable sets, like the set of real numbers. So this is something that Cantor proved in the 1870s, I believe. And this was sort of the introduction of the idea of infinite cardinalities into or infinite sizes of sets into mathematics. So in set theory, you can prove that the set of real numbers is not countable. So it's not the case that there's a one-to-one correspondence between the real numbers and the natural numbers. But then there's also this theorem, the Löwenheim-Skolem theorem from 1915, I believe, that shows that for any first-order theory, so including set theory, any first-order theory that has an infinite model has models of every infinite cardinality, including the countable cardinality. So these two theorems seem to contradict each other in a way. So you have one theorem that says that there is at least one set that is not countable, and then you have another theorem that says that you can have a model of that theory in which you can prove that at least one set is not countable, and that model is itself countable. So it seems like we have a contradiction between the two theorems. And there are some the various ways of sort of getting around this apparent contradiction, but in the sort of short version or rough version is that you have to be careful of what you mean of you have to avoid equivocation. So in stating the apparent contradiction, you have to pass from notions relative to one model and then move to notions relative to another model. And when you do so, there's a danger of equivocation, so treating two terms as the same even though they're actually different. And in particular, when you say that there's a model of set theory that's countable, then the meaning of the expression that a set within that model of set theory is uncountable is different than the meaning of the expression that a set is uncountable in a different model. So it only seems like a contradiction because you sort of abusively use the same expression to say that a set is uncountable in either the countable model or in some other model, and so that's sort of the explanation of why this is not a real contradiction. Hopefully that more or less makes sense. I tried to avoid some of the technicalities of the argument. But the bigger picture of the Skolem paradox has to do with our capacity to pin down the mathematical objects that we want to talk about using an axiomatic theory. So what it shows is that, or what we can take it to show, what some people have taken it to show, is that it's not possible using a system of first order axioms to pin down exactly what objects we're talking about when we do mathematics. So if we say the set of natural numbers or the set of real numbers, no first order system of axioms is capable of isolating or pinning down exactly the set of natural numbers or the set of real numbers that we want to refer to, and it's always there's always this possibility of these countable models or models that are not the intended model sort of creeping in, but and again there are a number of different ways of sort of dealing with this problem. And one is that in second order logic, so if you axiomatize set theory in second order logic, there is no Löwenheim-Skolem theorem, so it's not possible to construct models of any cardinality. And so in second order set theory, you can actually uniquely identify the uncountable sets. You don't have to worry about uncountable sets actually being countable in a particular model. So that's one way out of this sort of paradox. And so yeah, so this more general problem is what Cavailles points to here, is the right at the bottom of page 7. He says an exhaustive characterization of a model satisfying a system of axioms is impossible. So he takes it that we can't use a system of axioms to define the objects of a mathematical theory. We can't say that, here are axioms 1 through 10, and then the objects of our mathematical theory are just given through these axioms. We instead have to suppose the existence of some domain of objects, and then we can, within that domain, we can identify which of those objects satisfy the set of axioms. And so this is he characterizes this as a sort of anti-idealistic argument. So we can't assume that that mathematical thought is capable of creating its own objects through axioms. We have to, in some sense, take it that mathematical thought and systems of axioms come second. They come after the existence of the objects that they describe. So it's anti-idealistic in that sense. Right. So does that account of the Skolem paradox sort of make sense? Does everyone follow more or less what's going on in that paradox? Yeah, not hearing anything, I'm going to assume everyone is an expert on model theory now. So we can. Oh, sure.
I was going to say, it sounds like maybe the upshot for Cavailles is this point, the last thing you said about like formalization, that the mathematical thought can't be completely formalized because of these contradictions, or whether or not they're real contradictions, and first order modeling. Does that sound right?
Yeah. So what Cavailles takes to be the upshot of the Skolem paradox is that we can only ever come after the objects already exist. So mathematical thought can't create its own objects. Yeah, so it's not exactly the formalization that's the problem. It's this idea of having mathematical objects being given purely through a system of axioms in first order logic, yeah, so it's that sort of creation, the power of mathematical thought to create its own objects that he has an issue with here. All right, so let's go on to Lotman's part, which we'll see is in some ways a fairly different approach to Cavailles's approach, but I think we also can see some convergence that we might only get to in the discussion portion of the presentation. But maybe I'll let someone else read, since I've been talking for the whole time. So if someone would like to read the first page or so of Lotman's presentation.
I can read. What page does it start?
Page 8, about 3/4 of the way down.
Okay. Communication of Mr. Lotman. Having heard Mr. Cavailles, I am even more convinced that I do not agree with him, and I shall endeavor, during the few moments I have the floor, to clarify the points on which our views differ. Mr. Cavailles seems to me, in what he calls the mathematical experiment, experience, to attribute a considerable role to an activity of the mind, determining in time the object of its experience. There are therefore, according to him, no general characters constituting mathematical reality. On the contrary, the latter would assert itself at every moment in the history of mathematics as an event that is both necessary and singular. Hence the criticisms that Mr. Cavailles addresses to Platonism and mathematics, in the sense that Platonism would be identified with the theory of the existence in itself of mathematics. I agree with Mr. Cavailles on the impossibility of such a conception of an immutable universe of ideal mathematical beings. It is an extremely attractive vision, but of a really too weak consistency. The properties of a mathematical being depend essentially on the axioms of the theory where these beings appear, and this dependence removes them from the immutability that must characterize an intelligible universe. Nevertheless, I consider numbers and figures to possess an objectivity as certain as that which the mind encounters in the observation of physical nature. This objectivity of mathematical beings, which manifests itself in a noticeable way in the complexity of their nature, reveals its true meaning only in a theory of the participation of mathematics in a higher and more hidden reality, which constitutes, in my opinion, a true world of ideas. To make it clear how the study of the recent development of mathematics can justify the Platonic interpretation I have proposed, I must first emphasize what has been called the structural aspect of contemporary mathematics. These are mathematical structures, but we will later see how easy it is to go back from these mathematical structures to the consideration of dialectical structures embodied in actual mathematical theories. The structural aspect of contemporary mathematics is manifested in the importance of the role played in all branches of mathematics by the set theory due to Cantor, the group theory of Galois, the theory of algebraic fields of numbers of Dedekind. What characterizes these different theories is that they are abstract theories. They study the possible ways of organizing elements whose nature is indifferent. Thus, for example, it is possible to define global properties of order, completion, division into classes, irreducibility, dimension, closure, etc., which qualitatively characterize the collections to which they apply. A new spirit animates mathematics. Long calculations give way to the more intuitive reasoning of topology and algebra. Consider, for example, what mathematicians call existence theorems. That is to say, theorems that establish, without constructing it, the existence of certain functions or certain solutions. In a very large number of cases, the existence of the desired function can be deduced from the overall topological properties of a suitably defined surface. Thus, in particular, since Riemann, a whole geometric theory of analytic functions has developed that makes it possible to deduce the existence of new transcendent beings from the almost intuitive consideration of the topological structure of certain Riemann surfaces. In this case, the knowledge of the mathematical structure of the surface is extended in affirmation of existence relative to the function sought. If we reflect on the internal mechanisms of the theory to which we have just alluded, we realize that it establishes a link between the degree of completion of the internal structure of a certain mathematical being, a surface, in the existence of another mathematical being, a function. That is to say, in short, between the essence of a being and the existence of another being. These notions of essence and existence, as well as those of form and matter, of whole and part, container and content, etc., are not mathematical notions. Yet it is toward them that the consideration of effective mathematical theories leads. I call them dialectical notions and propose to call dialectical ideas the problem of the possible connection between dialectical notions thus defined. The reason for the relationship between dialectics and mathematics then lies in the fact that the problems of dialectics are conceivable and formulable independently of mathematics, but that any attempt at a solution to these problems is necessarily based on some mathematical example destined to support in a concrete way the dialectical connection studied. I have a question about this. One of the later kind of objections to Lotman. I think it was Hippolyte that said this, but somebody pointed out that it didn't. I think they objected that mathematicians probably weren't thinking of these notions in the terms in which Lotman is formulating them, like essence and existence, form and matter, and whole and part. But I don't think his point is that they think of these. They necessarily have these notions explicitly in mind. I don't know. It seems like they do guide the development of mathematics, but not necessarily. They're not necessarily consciously present in the minds of mathematicians who are working through the, I guess, concretization of the ideas that link these notions.
I think that's right. I think that for Lotman, I'm pretty sure he doesn't want to argue that individual mathematicians have to think about essence and existence in order to prove things about functional analysis or topology or whatever other particular mathematical domain, because that seems to be just false in a straightforward historical sense. So it seems pretty clear historically that mathematicians are perfectly capable of proving things about functions and numbers and surfaces and so on without having any awareness necessarily or thinking about any of these notions that Lotman is arguing is present here. So if we are going to be charitable in our interpretation of Lotman, I think we should assume that he's not saying something that's just obviously false in that straightforward way, and so we should assume that he's talking about notions that would guide or orient the development of mathematics, but without mathematicians being necessarily aware of those notions. And I think this is also borne out by the way that he analyzes different mathematical theories in his theses. He shows these notions, the ones that he lists here, the essence and existence, whole and part, global and local, and some of these notions. He shows how these notions are at work in different mathematical theories that don't have any obvious connection to each other. So there's a certain hiddenness that he points to in this text as well. So these notions are not obvious on the surface of the mathematical work. They're hidden in some sense behind that work. But I think overall, like so this text or this passage that we just read is probably the most explicit or the easiest entry point to Lotman's work and stating this thesis of the dialectics that governs the evolution of mathematics in this way, I think is I think this is the most explicit statement in his work. But here we don't have the sort of concrete evidence for this statement. He's just stating it as a thesis, but you have to look to his other works where he gives analyses of particular mathematical theories to find the evidence for this statement. And in those works, he shows how some of these notions are at work in different mathematical theories, and it's on the basis of that concrete examination of particular mathematical theories that he argues for this notion of the dialectic. It's not just sort of pulled out of thin air the way it might seem in this text. And then I'd also maybe it's worth commenting on this notion of structure that he points to, the structural aspect of contemporary mathematics. Lotman and Cavailles were both connected to the Bourbaki group, which was a group of mathematicians working in this time and was still active today in some form. But they wrote under the pseudonym Nicolas Bourbaki. They came up with this like invented biography of who this guy was. He was supposed to be like some Hungarian general or something that became a mathematician. Anyway, they right, thanks. They one of the sort of key ideas that they developed was this notion of mathematical structure, and they set out these textbooks of different areas in mathematics that sort of highlighted this notion of structure as being the key idea in mathematics, and mathematics as being oriented around structure. And so Lotman in 1939 is identifying what effectively ended up becoming like one of the key notions of mathematics in the rest of the 20th century, which is this notion of structure. And so he's already highlighting this notion before it has sort of fully become prominent and taken the center stage in mathematics. And then it's one that becomes more and more prominent over the course of the 20th century. So the interesting suggestion here from Angus in the chat, could these ideas and notions then be seen as an unconscious of mathematics? I think that's a possibility. I mean, Lotman doesn't use this term unconscious specifically, but I think the idea that the mathematical thought is guided by something that is not mathematical and that mathematicians are not aware of, I think it sort of lends itself to this vocabulary of the unconscious. And like just on that sort of connection between mathematics and psychoanalysis, like Lacan, of course, was interested in some of the developments of mathematics of that era. And there's a mathematician named René Guittard who is sort of like has a sort of Lacanian philosophy of mathematics. I don't know his work really. I have one of his books that I haven't had a chance to read yet, but he essentially argues for something like an unconscious of mathematics or unconscious thought as something in mathematics that plays a role in mathematics. So yeah, there's I think some interesting connections to make between Lotman's work and psychoanalysis. Just put that in the chat here. I don't think any of his work is translated, or I haven't seen any translations at least, but or of his philosophical work. I'm not sure about the mathematical stuff. But yeah, he has a sort of Lacanian approach to mathematics. Okay, so let's go on to the next page here. So if someone would like to pick up from the bottom of page 9, let us consider,
for example, the problem of the relationship between form and matter. It is possible to ask to what extent a form determines the existence and properties of the matter to which it can apply. This is a chief philosophical problem for any theory of ideas, since it is not enough to pose the duality of the sensible and the intelligible. It is still necessary to explain the participation, that is to say, by whatever name it is called, the deduction, the composition, or the genesis of the sensible from the intelligible. Yet mathematics provides precisely, in some cases, remarkable examples of the determination of matter from form. The whole theory of the representation of abstract groups aims to determine a priori the number of different concrete transformations capable of realizing actually an abstract group of given structure. Similarly, contemporary mathematical logic shows the close connection that exists between the intrinsic properties of a formal axiomatic and the extension of the domain of individuals in which this axiomatic is realized. We therefore have here the spectacle of two theories as distinct as possible from each other: the theory of the representation of groups and mathematical logic, which nevertheless present between them close analogies of dialectical structure, those which come from there being, both of them, particular solutions to the same dialectical problem, that of the determination of matter from form. I indicated above that the distinction of an ideal dialectic and an effective mathematics should above all be interpreted from the point of view of the genesis of mathematics from dialectics. Here is what I mean by this. Dialectics in itself is pure problematic, a fundamental antithetics relating to couples of notions that seem at first glance to be opposed, and about which nevertheless arises the problem of a synthesis or a possible conciliation. This is how, for example, I considered in my thesis the problem of the relationships between the local and the global, the extrinsic and the intrinsic, the continuous and the discontinuous, etc. It then turns out exactly as in Plato's Sophist, that the contraries do not oppose each other, but that they can be composed with each other to constitute those mixtures that are mathematics. Hence the need for those subtleties that are so complicated, of this unpredictable picturesqueness, of those obstacles that sometimes one overcomes and sometimes circumvents, of all this historical and contingent becoming that constitutes the life of mathematics, and which nevertheless presents itself to the metaphysician as the necessary extension of an initial dialectic. One passes insensibly from the understanding of a dialectical problem to the genesis of a universe of mathematical notions, and it is at the recognition of that moment, when the idea gives birth to the real, that in my opinion, mathematical philosophy must aim. I have tried to show, in a booklet that was published by Librairie Hermann after my thesis, the analogy of these conceptions and those of Heidegger. The extension of dialectics into mathematics corresponds, it seems to me, to what Heidegger calls the genesis of ontic reality from the ontological analysis of the idea. One thus introduces, at the level of ideas, an order of the before and after, which is not time, but rather an eternal model of time, a schema of a genesis that is constantly being carried out, a necessary order of creation. It seems to me that the problem of the relationship between the theory of ideas and physics could be studied in the same way. Consider, for example, the problem of the coexistence of two or more bodies. This is a purely philosophical problem, which we will say Kant posed, rather than solved, in the third category of relation. It turns out, however, that as soon as the mind tries to think what the coexistence of several bodies in space can be, it necessarily engages in the still unsolved difficulties of the problem of n bodies. Let us also consider the problem of the relationship between movement and rest. One can abstractly pose the problem of knowing whether the notion of movement has meaning only in relation to an absolute rest, or whether, on the contrary, there is rest only in relation to certain changes. But any effort to solve such difficulties gives rise to the subtleties of the theory of special relativity. One may also wonder to which of the two notions, of movement and rest, it is necessary to attach a physical meaning. And this is a point where classical mechanics and wave mechanics are opposed.
Right. So there's a couple sort of technical points that are maybe worth elucidating before we sort of go into the more philosophical content here. So in the last little bit, so he brings up, he mentions in passing here the problem of n bodies, and this has to do with this is a problem in mechanics that I don't know like the details very well, but effectively the n body problem is that the motion of three or more bodies relative to each other that are attracted to each other through gravitation or some other force. The motion is chaotic. So like in a simple system, you can sort of analyze the motion of each individual body, and then you analyze the motion independently of the other bodies, and and then you can sort of, as a second step, add on the interaction terms. So you can say that body one moves in a certain direction, and then body two is moving in a different direction, and then secondarily you look at the interaction between those two bodies and see how that changes the direction in which each of them is traveling. But when you get to three or more bodies, what happens is that it's not actually possible to decompose the movement in this way and sort of treat each body independently, and then as a second step treat their interaction. And so the effect of body one on body two sort of feeds back into the effect of body two on body one, and you can't isolate them from each other. So this applies even to relatively simple systems like the solar system. So it's actually not possible to prove that the solar system is stable. So it could be the case that after a certain period of time, however many millions of years, that the bodies, the planets, will either fall into the sun or will escape from the gravity of the solar system, or do all kinds of weird things. So this is a sort of general problem in mechanics, and so what Lotman is arguing here is that we can sort of, in a philosophical sense, we can abstractly pose the problem of what it means for two bodies to be in relation to each other or to coexist, in the more general case. But as soon as we start trying to make this problem, trying to present a solution to this problem in a precise way, we end up in doing mechanics and entering into this n-body problem. And then likewise, if we set out a philosophical problem about movement and rest, and we want to know, is there such a thing as absolute movement, or is movement always relative to a certain frame of reference? And this was a debate that sort of characterized physics from I guess the 17th century up until the beginning of the 20th century. And there's a famous set of papers, the Leibniz and Clarke debate, where Clarke was a friend of Newton, who defends the absolute conception of space and time, and therefore of movement, whereas Leibniz has a relative conception of space and time and of movement as well. And so you can set out philosophical arguments for one or the other positions. You can say either that there is such a thing as absolute movement, or you can say that movement is only defined relative to a frame of reference. But once you start entering into some attempt to solve this problem in a precise way, then you end up with a mathematical theory of movement, and that leads you into, or Lotman here suggests that leads you into special relativity, in which movement is always relative to a frame of reference. And so that doesn't make sense in special relativity to say that a body is moving in an absolute sense. It only makes sense to say it's moving relative to some other body. For inertial movement, I should say, for non-accelerated movement. So these types of problems are instances that he gives of how what seems like a philosophical problem, or what can be set out as a philosophical problem, can only really receive a solution in developing a mathematical theory, so it's not possible for Lotman, it's not possible to sort of come up with a philosophical argument that would solve once and for all whether movement is absolute or relative. Instead, you have to develop a mathematical theory of movement in which you sort of decide whether to take movement as absolute or relative, and then you continue to develop the theory based on that decision. And then these different mathematical theories have relations to each other through these notions. So there's so the notions are these concepts that appear in various mathematical theories that sort of guide the development of mathematics without mathematicians being aware of them. And then, so a couple of the problems that he raises, or the questions that he raises here, are the relationship between these notions, or the realm of the ideal dialectic, and so the relation between that realm and mathematics itself, or the generation of mathematical theories. And he points to the relationship between form and matter within mathematical theories as being a sort of model of how this works. So there's in particular mathematical theories, you can find like he gives the example of representation of groups, and then model theory as instances of this. So you have some sort of abstract structure, and then you can derive from this abstract structure. You can show that anything that fills that structure has to have certain properties, and you can look at the relationship between the properties of the objects that fill the structure, and then the structure itself. And there's sort of whole domains of mathematics that are dedicated to this type of pursuit. And so this same type of relationship that occurs within mathematics is how we can picture the relationship between the ideal dialectic and mathematics as an instantiation of that theory. So there's this sort of reciprocal relationship between the dialectical ideas and the concrete mathematical theory. So there's certain properties of mathematical objects that they have to have in order to be able to instantiate the dialectical ideas, so these ideas have to be instantiated in particular mathematical theories in order to have existence. Maybe I thought, Angus, you might bring up the bit about Heidegger, the reference to Heidegger here. I see you posted something in the chat about that. Yeah, I think the reference to Heidegger here, and this is not the only place where he makes reference to Heidegger. He does so in another article as well. But it's a bit of a strange reference, I think. Because I don't think Heidegger ever uses this exact phrase, the genesis of ontic reality from the ontological analysis of the idea, or that sort of set of notions together. In Being in Time, he does sort of want to show how these ontic structures of Dasein are rooted in ontological structures, or that there's this more fundamental level of ontological structures in part 2, or division 2, I should say, of Being in Time. but I don't think he uses this term, the genesis, and in particular, he doesn't use the term idea. So there's a bit of a, I don't know, sort of constructive interpretation going on here that Lotman is kind of reading into Heidegger and what he wants to find there, I think, as opposed to having like a faithful interpretation of Heidegger.
Yeah, I thought that the reference, I agree with what you just said on the idea of the genesis of the ontic from the ontological not really being in, at least in being in time. But I thought that it made more sense in terms of like understanding and interpretation in Heidegger, where this kind of preconceptual projection out of which an intelligible concept is developed, which would seem to line up with what Lotman is saying here with the pre-mathematical ideas and their instantiation in mathematical theories.
There's a couple of other places that I would have thought that he might have mentioned. There's the metaphysics of logic, I think, where Heidegger is engaging directly with Leibniz, and the lecture series, the Identity and Difference book as well. Those are both places where he is sort of talking about part-whole relations, like kind of how you gather, how a multiplicity kind of forms into an identity as a result of a sort of careful sort of phenomenological description of part-whole relations. And listening, like sort of reading this and then seeing mention of Heidegger puts me in mind of those two places. But yeah, I mean, I totally agree with the diagnosis that it's basically a kind of constructive sort of analogy into Heidegger's work rather than something that's kind of dealing with the ideas directly.
I think I'm just trying to remember. I think those texts were not published at the time that Lotman was writing. Like the lecture courses were mostly published after World War II, and
Got it. Okay.
yeah. So I think he wouldn't have had those texts available. He makes reference to the introduction to, or sorry, the not introduction to metaphysics, the fundamental concepts of metaphysics, I think is the name of the text. The one where he talks about the nothing, how the nothing annihilates, and the one that Carnot. Yeah, so he makes reference to a couple of the texts, and then I think being in time as well, possibly. But the texts that he refers to are all from the 20s and 30s, and so there was a limited amount of Heidegger material that was available at that time.
Makes sense.
But yeah, so like I think it's sort of open to question whether, like, even if Lotman did have all of Heidegger's lecture courses and stuff available, would he have modified his interpretation of Heidegger or his use of Heidegger? I'm not sure. Like, I don't think his goal is really to do Heidegger exegesis. It's instead he wants to make use of some of Heidegger's concepts in this specific way here. I think also, Angus, going back to your comments about the connection with understanding and interpretation in Heidegger, I think that's an interesting suggestion, because Heidegger always talks about it's something that doesn't come up that often, but whenever he talks about sciences, he always talks about the sort of preconceptual understanding of the domain of that science. So like physics has a sort of preconceptual understanding of nature on the basis of which certain objects get incorporated into theoretical, into the explicit theoretical understanding of what nature consists in. And I think that's something that we can compare to some of these notions, the dialectical notions, for Lotman. Like these notions are sort of these pre-mathematical principles that govern the formation of a mathematical theory, in the same way that the preconceptual awareness or principles for Heidegger governs the formation of a physical theory or a theory of theology or whatever other particular domain. Okay. So we can continue. I can read the next little bit. I'll finish the Lotman part and then go on into the discussion. Actually, no. I think I'll just finish the rest of the Lotman part and then we can stop for there and then continue afterwards. Okay, so we're at the top of page 11. Yeah. Okay. The former. So I'll go back one sentence just to clarify that reference. One may also wonder to which of the two notions of movement and rest it is necessary to attach a physical meaning, and this is a point where classical mechanics and wave mechanics are opposed. The former considers the wave as a real physical movement. For the latter, on the contrary, the wave equation appears only as an artifice intended to highlight the physical invariance of certain expressions with respect to certain transformations. It thus appears that the theories of Hamilton, of Einstein, of Louis de Broglie take on their full meaning by reference to the notions of movement and rest, of which they would constitute the true dialectic. It may even be that what physicists call a crisis of contemporary physics, struggling with the difficulties of the relationships of the continuous and the discontinuous, is a crisis only in relation to a certain rather sterile conception of the life of the mind, where the rational is identified with unity. On the contrary, it seems more fruitful to ask whether reason in the sciences does not rather have for its object to see in the complexity of reality, in mathematics as in physics, a mixture whose nature could only be explained by going back to the ideas in which this real participates. We thus see that the task of mathematical philosophy, and even of the philosophy of science in general, should be: one must build the theory of ideas, and this requires three kinds of research: that which emerges from what Husserl calls descriptive eidetics, that is to say here, the description of those ideal structures embodied in mathematics whose richness is inexhaustible. The spectacle of each of these structures is each time more than a new example brought in support of the same thesis, because it is not excluded that it is possible, and this is the second of the tasks assignable to mathematical philosophy, to establish a hierarchy of ideas and a theory of the genesis of ideas from each other, as Plato had envisioned. It remains finally, and this is the third of the tasks announced, to redo the Timaeus, that is to say, to show within the ideas themselves the reasons for their applications to the sensible universe. These seem to me to be the main goals of mathematical philosophy. Right, so he begins with this opposition between classical mechanics and wave mechanics, and wave mechanics is an alternate formulation of what became quantum mechanics, and we saw this opposition to some extent in the Simondon reading when we were looking at physical individuation. So in classical mechanics, a wave is a real physical displacement that occurs within some sort of medium. So like a sound wave is a displacement of air, for example. And then, of course, this leads to the conception of light. So the conception of light as a wave leads to the conception of the luminiferous ether, which would be some sort of medium in which light waves would propagate. And there were some difficulties with that conception that led to the development of special relativity at the beginning of the 20th century. Whereas in wave mechanics or in quantum mechanics, in the standard interpretation, the wave function is a sort of mathematical principle governing the evolution of the system, but it's a wave in configuration space and not in physical space. So the wave is not taken to be a real physical wave. It's this sort of mathematical principle that governs the evolution of a system, but it's not a physical wave. And then so we saw in discussion of Simondon that there are these alternate theories of quantum mechanics, namely the pilot wave theory and the double solution theory, in which there is a real physical wave that corresponds to the wave function, and so this is an alternate conception of quantum mechanics that Lotman doesn't take into consideration here, probably because at this time in 1939 those theories were considered, or in the physics community, those theories were considered to be refuted at this time. We talked about this in the Simondon discussion, that there was the Solvay conference in 1927, where Louis de Broglie he presents the pilot wave theory, and then he receives some objections that he doesn't really have a good answer to, and then he gives up that theory. And then later, von Neumann presents an argument that is meant to show that theories of that kind are impossible, that you can't have a hidden variables theory of quantum physics. And then it was only in 1952 that David Bohm showed that it actually is possible to have a hidden variables theory of quantum mechanics that is adequate, that captures the predictions of standard quantum mechanics. But that's sort of an aside. But what Lotman is pointing to here is that this notion of a crisis of physics that was still prevalent in the 30s, this idea that physics is going through a crisis because some of these fundamental concepts like space and time and what matter is and so on, that these concepts are sort of being overturned and reinvented, and no one really knows how to interpret them anymore. For Lotman, this crisis is really a reflection of what he calls a sterile conception of the life of the mind, and so he thinks that this conflict of these opposed notions, where you have seemingly contradictory ideas in quantum mechanics as opposed to general relativity, for example, these opposed notions are part of a dialectic that is prior to the mathematical theory in question, and so we shouldn't see the opposition between these notions as a crisis, but instead we should be trying to work out mathematical theories that involve some sort of mixture or synthesis of these opposed notions. And then we have this last paragraph of his presentation, which is I don't know, it's hard to express exactly, but it's very evocative. I think it sort of, especially given the fact that he, of course, was not able to work out this program for mathematical philosophy because he was executed by the Nazis in 1944, but he sets out this program for mathematical philosophy, these three tasks that he thinks that mathematical philosophy should be pursuing. So the first one is this descriptive eidetics. So it's a description of those ideal structures embodied in mathematics. So it's just this is the task that he had pursued in his two theses. So just looking at concrete mathematical theories and analyzing the different structures, these ideal notions that are at work in these mathematical theories. So that's the first task. And then the second one is dependent on the first. So it's not just the case that you can identify different dialectical notions in various mathematical theories. You can also develop this hierarchy of these dialectical ideas from each other in relation to each other. So and he described this as a genesis of ideas. This is something that he didn't really have a chance to pursue in much detail, but it would be an account according to which different dialectical ideas would generate each other. So you would have some dialectical idea that would form the basis for another one. And so we have this notion of a genesis, not as something that occurs within time, but this sort of extratemporal genesis of ideas from each other. And then finally, the third task is, so he describes this as redoing the Timaeus, and so the Timaeus was Plato's dialogue where he gives an account of the creation of the world. So the demiurge, this sort of divine entity, puts together the world by using various mathematical principles to construct the world. Simon, or I keep saying Simondon, Lotman here, he argues that we need to sort of do the same thing. So have an account of the genesis of physical reality from mathematical principles, in a similar way to how Plato had this account. Of course, it would have to be updated for contemporary physics and contemporary mathematics, but it's a genesis of the physical worlds from this ideal world. This ideal world of the dialectic. So you have a genesis of mathematics from the ideal, and then you have a genesis of the physical world from the ideal as well. Okay, so let's go on to the discussion portion of the presentation. I think what would make sense is to read. Let me see how long this is. So to read each intervention as one go. So if someone would like to read Mr. Cartan's presentation or intervention, I should say.
I can read this. Okay. Discussion, Mr. Cartan. I'm quite embarrassed because I am a little in the situation of Mr. Jourdain, who used to speak in prose without suspecting it. Mathematicians, at least a number of them, among whom I place myself, are hardly in the habit of thinking about the philosophical principles of their science. When they hear a philosopher talk about them, they are interested. They are not sure how to respond to the considerations he develops. Obviously, I know the thesis of Mr. Cavailles and the thesis of Mr. Lotman, since I was part of the jury of both, but my situation is different. Previously, I was on the right side of the barricade, while today I'm on the other side. I did not quite understand what opposition there was between the 2 points of view of Mr. Cavailles and Mr. Lotman. Points of view which seem to me to be different rather than opposing. I have the impression that Mr. Cavailles's considerations relate to the very substance of mathematical thought, while Mr. Lotman's considerations relate more to the current state, not of the whole of mathematics, but to a certain number of mathematical theories. And in this regard, there are obviously a number of statements by Mr. Lotman that are of particular interest to me, those concerning the relations between the local and the global, for example. Certainly, these relationships arise in an important part of mathematics. The theory of functions, in particular the functions of real variables as it has been conceived for 50 years, cannot raise the problem of the relationship between the local and the global. The functions envisaged are too general for their global properties to be deduced from their local properties. But there's a class of functions for which the relationship of local and global is basically the essential part of the problem. These are the analytic functions of complex variables whose global properties are determined by local properties. For quasi-analytic functions which have recently been introduced, something similar happens. When we know at a point the values of the function and those of its successive derivatives, it is completely determined in its entire field of existence. In geometry, it is especially geometry that Mr. Lotman was thinking of. There are also extremely important problems for which the relationship between the local and the global arises. If we take, for example, a space, a small piece of this space, in a space, a small piece of this space, is it possible by the knowledge of this small piece to deduce the knowledge of the whole space? Of course, it must be assumed that this space has fairly simple global properties, without which this problem would not make sense. These are, on the surface, problems of pure geometry, but in reality, there are also problems of analysis. Let there be, for example, a portion of Riemannian space. If you assume that the functions that intervene to define the space are analytical, you will have a problem extremely interesting, which is the following. Knowing a small piece of Riemannian space defined analytically by its differential form, to what extent can we deduce the global properties of this space? It may happen that this small piece cannot be extended until it formed a complete space. In general, that is what happens. If it can be extended to form a complete space, it can be extended in only one way with certain restrictions. This is therefore a problem of the relationships of the global and the local, which is not defined simply by its geometric statement, but which is related to the existence of purely analytical properties in the definition of the piece of the space. Similar considerations could be developed about the relationship between the intrinsic and the extrinsic. Given a surface immersed in a certain space, do the assumed to be known intrinsic properties of the surface imply limitations of the properties of the space that contains it? There are some extremely interesting problems here, but it should be noted that they depend not only on the geometric position of the problem, but on its analytical position. Mr. Lotman gave a number of other examples of such problems: form and matter, group theory. All this is very interesting, but I do not know to what extent it justifies Mr. Lotman's general thesis, because I do not quite understand what dialectics is, and I am obliged to remain on a purely technical ground. I do not have the impression that Mr. Lotman's considerations contradict those of Mr. Cavailles. I have the impression that Mr. Lotman considers some particular problems of modern mathematics and a number of philosophical problems. I think I am, on the whole, in agreement with him, but unfortunately I am unable to discuss this with him in this field. In any case, with regard to the character of mathematics having an autonomous and unpredictable development, I believe that one cannot go against this statement. However, history teaches us that there has been in the history of mathematics, which I've lived, certain predictions of the future. There was in 1900 a conference by Hilbert on the future problems of mathematics, an extraordinarily remarkable conference because precisely he put his finger on the problems that were to arise in the development of mathematics for 50 years at the least. And he anticipated precisely the most important problems that have actually arisen. On the other hand, one could find lectures by eminent scholars on the future of this or that branch of mathematics, in which these scholars did not foresee at all what was going to happen. Certainly, the development of mathematics is something unpredictable in itself, and when one reaches a certain age, one realizes that certain theories, after 20, 30, or 40 years, take on a completely unexpected development, and that the point of view from which we end up envisaging them is quite different from the initial point of view. However, we are obliged to recognize that these are internal necessities that have been revealed in the further development of these theories. I'm thinking, for example, of topology, the science which barely existed half a century ago, and which takes on a new aspect every day in a completely unexpected development, penetrating deeper and deeper into all branches of mathematics. I think this idea that in some cases the predictions of mathematicians are accurate, and in some cases they are not, is exactly like prospective contingency, right? I don't think the fact that Hilbert got it right and others got it wrong means that these things aren't contingent looking forward.
Yeah, I think if we look back at Cavailles's text, he does mention intuition of mathematicians as having this capacity of predicting where the solution of various problems is going to come from. So mathematicians who are working in a particular domain, they often are able to pose conjectures, even if they can't prove something. They can say that that we have a lot of reason to believe that this proposition is true or false, and then that sort of sets a problem for other mathematicians or the same mathematicians to eventually prove or refute that conjecture. And so I don't think the contingency of mathematical history is in contradiction with this capacity for mathematicians to make conjectures or to have this intuitive sense of where the development is going to go in the future, because it's never it's not like stating a conjecture is something quite different from proving a conjecture, and so you can't sort of read off the proof from just the statement of the conjecture. And so Hilbert was able to point to these 27 problems, or sorry, I think how many problems? 23 problems. Sorry. He was able to point to these problems that sort of ended up being many of the key problems of 20th century mathematics, and some of them are still open today. But in doing so, he didn't sort of set up future mathematicians to just sort of mechanically derive the results from the statement of the problem. So it still takes a huge amount of creativity and introduction of new concepts and techniques to solve these problems that he stated. And so this, I think the contingency is sort of, it's maybe a bit of a misstatement to try to link this contingency with predictability, or at least they aren't. They don't sort of coincide. The question of contingency and the question of predictability, because there is some a certain degree of predictability in mathematics, in the sense that you can sort of have this intuitive sense of where problems are which problems are important, and what types of solutions certain problems are going to have. But that doesn't mean that the actual solution of that problem is something that can just be derived in a mechanical way from the statement of the problem. I think this intervention here is an interesting one, precisely because Cartan was one of the leading French mathematicians of the time, and he was also on the jury of both Lotman and Cavailles's theses, or the committee, I guess I should say. And his relation to, or his questions about Lotman's idea of dialectics, I think, is an interesting one, because he seems to be in agreement with a lot of the actual concrete analyses that Lotman gives. So the presentation of the concepts of the global and the local at work in different mathematical theories, or intrinsic and extrinsic, and so on. He seems to agree with a lot of that analysis that Lotman gives, but he's sort of skeptical of he at least reserves judgments about the dialectical, the idea of dialectics, and he doesn't even go into the question of whether this dialectics is something extra mathematical, or whether we have to think of mathematical development as being sort of autonomous and self-contained. So there's, I think it's interesting that he has some sympathy for these ideas, and he's obviously not opposed to the idea of this philosophical analysis of mathematical theories, since he was, a member of the committee for both of their theses. But he's still sort of reticent about some of the more speculative sides of Lotman's development. Okay, so let's go on to Lévy's contribution. If someone else would like to read, it's about a page long, so we can read that in one go. If someone else would like to read.
I can go again. Mr. Paul Lévy, I could first of all repeat what Mr. Cartin just said just now. I'm a little disconcerted when I hear philosophers talking about the science that I study in a language that I am not used to. I struggle to follow them, and I'm not sure I understand everything they say. I think I'm just about certain I've understood some of it, but I'm equally certain I didn't quite understand some things. I cannot therefore express an opinion on all the issues that have been raised. I can only present a few thoughts that were suggested to me by Mr. Cavailles' conference, and I believe that they do not miss the point. If I am wrong, I apologize. I think I am somewhat in opposition to Mr. Cavailles, yet his conclusion reassured me when he said that there were in the becoming of mathematics some inner necessities which were revealed. I believe that the development of mathematics, while having a great contingency, it goes without saying, presupposes much deeper inner necessities. Naturally, it was impossible to predict that such a theorem was to make its appearance at such a date in history, but inner necessities play a very great role, and there are theorems of which I can tell you. If such a scholar had not found such a theory at such a time, and if such a theorem had not been proved such a year, it would have been discovered within 5 or 10 years. I give as proof that a very large, 69, number of theorems were, at very short intervals, discovered separately by different scholars because they responded to a need for the development of mathematical thought at that time. Therefore, this allows me to think that, when a certain mathematical theory has begun, a superior mind can predict a little in which direction it will develop. I take as a concrete example one of the mathematical theories whose philosophical aspect has attracted the most attention, the theory of the integral, as the modern theory of sets has made it possible to build it. It was Mr. Lebesgue who gave the notion of integral its final form, and currently you all know that this integral is an essential tool of mathematics. It is so essential that, without a doubt, if Mr. Lebesgue had not existed, his integral would still be, today, something discovered a long time ago. I do not think I diminish Mr. Lebesgue's merit. On the contrary, I believe that I am merely increasing it by saying that he has highlighted a concept that was necessary for the further progress of science. Would M. Émile Borel, who was already working in this area, have developed this theory? Would it have been given to another of his students to do so? I don't know. But after the work of Jordan and Mr. Borel, given the current level attained by the whole of humanity and the number of researchers specialized in the field of mathematics, I believe that it was necessary and inevitable that, within 10 or 15 years, the theory of Lebesgue integral would be established. And in this vein, I believe to a certain extent that the development of mathematics is predictable. Of course, it must not be denied that, on the other hand, certain discoveries constitute an unpredictable leap in the development of science, coming before their time. It happens that their importance is recognized only after a longer or shorter time. On the other hand, it is certain that there are, among mathematicians, geometers, and algebraists, some operate in one branch of mathematics, others in another. It would have been conceivable that the human species contained only geometers and not algebraists, or vice versa. It is also possible that a further development of humanity will allow certain brains to devote themselves to certain branches of mathematics that we cannot conceive of at present. On the other hand, there is one point on which the two speakers agreed, and to the extent that I understood them, I am a little surprised. For me, mathematics would have no reason to exist if its object were considered non-existent. When I say that the product of two numbers is independent of their order, it is, 70, something that is true, regardless of the fact that I state it. This is not true only in my thinking. I take a simple example which can be verified objectively. I have rectangular boxes comprising a number of rows and columns. I have a certain number of marbles that I want to put, and I want to put one in each box. Well, the same number of marbles will be enough, depending on whether I fill the boxes by rows or by columns. I take this very simple example because in others, it would be difficult to find a material interpretation to verify the accuracy of a theorem. For me, the theorem pre-exists. When I try to prove whether a statement is true or false, I'm convinced that it is true or false in advance, regardless of the chances I have of discovering it. Let's take another problem. Is Riemann's hypothesis about his function accurate or false? I believe that most mathematicians are convinced that it is accurate, although no one has proved it. And I think that all the mathematicians who are in this room will agree that, though we may never get there, this hypothesis is in itself true or false, even if we cannot know whether it is true or false. If I understand your language correctly, you will express my position by saying that I am a Platonist, but I can't imagine what might make me abandon this point of view.
Yeah, in the last bit there, maybe I should have written it out in letters, but it's the zeta function. So this is a famous function that Riemann had identified that it has the property of giving an estimate of the number of prime numbers in a certain range. So if you take like the numbers between 1,000 and 10,000, you can use the Riemann zeta function to give an estimate of how many prime numbers there are in that range of numbers. Anyway, there's an open problem having to do with proving that this estimate is correct. That if you continue to evaluate the function, then you get better and better estimates of the number of prime numbers less than a given number. And so that's an open problem that has been open since the mid 1859. Yeah. There's a weird sort of thing in the French text. It looks like there's an error of the stenographer, but I'm not 100% sure what happened exactly. But it certainly seems like he's referring to the zeta function in this passage here. But what he's arguing for is essentially what he calls the Platonist position, that is essentially just the position that mathematical propositions have a truth value independent of our capacity to prove or to know what that truth value is. I think it's interesting that this is sort of where he goes to, because this question was not really one that either of the presentations was devoted to. Like they weren't setting out to prove either that or to argue that either mathematical propositions do have a determinate truth value independent of our knowledge of them, or the contrary. This wasn't really a problem that was a core question of either of their presentations. So I think it's interesting that as a mathematician who, as he says, he doesn't really, he's unsure of how to understand philosophical analyses of mathematics. His sort of first thing that he latches onto is this question of whether mathematical propositions have a determinate truth value independent of our knowledge of them. So he for whatever reason, this question seems to be one that mathematicians gravitate towards, even when there's the philosophical discussion is not really oriented towards that question. And I think there's also in a little bit earlier in his intervention, there's this question of predictability, this whether or not it's possible to predict where mathematics will evolve, and he takes the position that that this contingency that we find and that Cavailles pointed to is sort of illusory, or that the necessity side is more prominent or more important, and so he points to the way that in a number of instances you find that more than one mathematician proves a theorem at the same or roughly the same time, independently of each other. And so what he takes this to show is that there's a certain necessity that is more fundamental than the apparent contingency. So the contingency is only from the perspective of it's only due to our ignorance, whereas the necessity is a real necessity that underlies the evolution of mathematical thought. So he's contesting the reality of the contingency side of Cavailles's dialectic. And I think maybe more on that last point is that I think it's also a bit surprising from a mathematician to make that argument, because it is effectively denying that mathematicians are creative when they solve problems, and so if you hold that the contingency side of the dialectic is only a result of our ignorance, then you're effectively saying that mathematicians who solve problems and prove theorems are just sort of working out the necessary consequences of various mathematical principles, rather than having some sort of creative development of mathematics through invention of new concepts and new techniques. Okay, so let's go on to the next intervention here from Mr. Fréchet. Let's see, how long is it? This one's a bit long, so maybe we can break it up into two. But I'll start reading, and we'll see if there's a natural stopping point. Okay, Mr. Fréchet. I will begin by agreeing with an observation that has just been made before me successively by Messrs. Cartan and Lévy. For a mathematician who devotes the main part of his activity to mathematics, it is extremely difficult to follow in all their nuances the presentations, though so informative, of Messrs. Lotman and Cavailles. Perhaps the difficulty in discussing them is not so much in what they said, as in the prior need to understand exactly what they meant. Before going into a few details, however, I would like to say that, in any case, I admire the virtuosity with which they handle not only philosophical language, but also mathematical language. We are immersed in mathematics and, at least as far as I am concerned, completely ignorant of the subtleties of philosophical language and the nuances that differentiate certain philosophical theories, while our distinguished colleagues seem, on the contrary, both to operate with ease, not only in philosophy, but in mathematics. Finally, they know about the technique, about the results of certain parts of mathematics, many things that personally I do not know. Precisely for the reasons I have indicated above, I do not want to repeat one by one the various subjects they have dealt with. But there are 2 or 3 points on which I may have understood their thesis and on which I would like to say a word. First of all, there are 2 questions that are related, at least in my mind, and to which I could perhaps give an answer. Mr. Cavailles indicated that, in his opinion, mathematics is an autonomous science. Personally, I do not think so. Everything depends, first of all, of course, on what is called mathematics. Many people call mathematics the set of deductive theories that make it possible to pass from a set of properties and axioms to certain theorems. This is, without doubt, the most specific part of mathematics. But it seems that if we stopped there, not only would mathematics be reduced to a machine of transformations, and in this case its role would still be very useful, but that it would be limited to transforming, so to speak, emptiness into emptiness. I believe that to justify the existence of mathematics, it is essential to show in it an instrument that was invented to help man to know nature, to understand it, and to predict the course of phenomena. The notions that seem to me the most fundamental in mathematics are all notions that do not come, in my opinion, from our intelligence, from our mind, but that are imposed on us by the outside world. I will mention, for example, the whole number, the line, the plane, the ideas of speed, force, certain transformations such as symmetry, similarity. These are notions that were not present in our minds, but that were imposed on us by the consideration of the world around us. We translated these external realities into words, axioms, definitions, which represented them only approximately, of course, which were simpler to be more manageable, but which still had their source in the outside world. These fundamental notions that we find at the origin of mathematics are constantly added others, introduced by the development of the physical sciences. The notions of work, of momentum, of a force, for example, have only been defined, to my knowledge, for 2 or 3 centuries. Many other notions that I could indicate, such as differential equations, were introduced only in modern times as a result of the development of physics, mechanics, astronomy, etc. In addition to these notions whose study is, so to speak, imposed on us, other notions of a different nature have been introduced in mathematics. These are those which are due to the internal activity of this science. They seem to me much less fundamental than the others, having been imagined to facilitate the task of the mathematician with a view to the solution of the problems posed from outside. To give elementary examples, let us mention transformation by inversion, transformation by reciprocal polars. These are 2 transformations that, as far as I know, have not been imposed by examples taken from nature. They are the artifices of mathematicians that provide means of investigation. Similarly, I think that the introduction of complex numbers has provided an extremely powerful instrument more quickly. One could cite many other examples. In elementary geometry, one introduces the consideration of supplementary trihedra. Here again, I don't think there is a real phenomenon that forces us to consider these supplementary trihedra, but it does provide a convenient way to transform one proposition into another in elementary geometry. I see, therefore, in the examples I have just mentioned, 2 categories of notions, some that fall well within the category of autonomous mathematics, and others, on the contrary, that do not seem to me to be reconcilable with the idea of an autonomous mathematics. On the contrary, this leads me to agree with Mr. Cavailles, for reasons different from his own, it is true, on the unpredictability of mathematics, placing myself at a point of view which, moreover, is entirely reconcilable with that presented by Mr. Paul Lévy, and which would seem to lead to a contrary conclusion. Mr. Lévy gave many examples where problems could not fail to be solved by mathematics, and in this sense, mathematics was predictable because these were problems that mathematicians had posed for the internal development of mathematics. But there are constantly, in the development of sciences outside mathematics, problems that arise that are imposed on mathematicians, that mathematicians are asked to solve and that give them new ideas, forcing them to introduce new notions. And those ones are unpredictable. We do not know, we cannot even imagine the nature of the problems that in 50 years' time, technology or physics may pose to mathematicians. Perhaps we will have the means to solve these problems by drawing on the existing arsenal of mathematical theories. Perhaps we will have to create new mathematical tools. There is an impulse from outside and whose interventions are of an unpredictable nature. That is what I wanted to say about autonomy and non-predictability of mathematics. Let's stop here. Now I'll mention this footnote. So he added these footnotes to the stenography afterwards. So he says, I developed these 2 points, among others, in a report presented in Zurich in December 1938 on the question of the foundations of mathematics and general analysis at a colloquium organized by the International Institute for Intellectual Cooperation, whose debates will be published by that institute. So here, the question of this autonomy of mathematical science, of mathematics, is raised in connection with the relationship between mathematics and physics in particular, but other sciences in general. And so he makes a distinction here between particular problems that are posed internally to mathematics that mathematicians raise for themselves, and then on the other hand, problems that arise from external domains that are sort of imported into mathematics. And he argues that the existence of these problems posed by physics or other external domains makes mathematics not autonomous in the sense that Cavailles had used the term. And this also has to do with the question of the contingency and necessity of mathematical development, because he argues that it's only these internal problems that have this sort of necessary development. That the necessity side is a characteristic of mathematical problems that are posed internally to mathematics, whereas the contingency side would be a product of these external problems that are imported into mathematics. And so for him, the distinction between necessity and contingency is not a dialectical problem. It's not something where we have to hold on to these two contradictory ideas at the same time. It's a question of two different aspects or two different sets of problems in mathematics. So for him, he wants to sort of reduce what for Cavailles is this dialectical notion or something that is only graspable in philosophical thought. He wants to reduce this to just a distinction between particular domains in mathematics, which we could call like pure and applied mathematics, I guess. I think we should probably stop here rather than going on to the next bit of the discussion. Just because, in terms of time, and there's about a page left of this of Fréchet's intervention, so we can save that for next time, and then we can continue from there. And then let's see, Lotman and then Hippolyte. And then after a couple pages, starting from page 20, we get from 21 we get Cavailles and Lotman's replies to the other interventions. We hopefully we should be able to finish the text next time, I think. I managed to get a hold of the translation, the other translation that I mentioned in the chat a couple weeks ago, so as I suspected, it's only fragments of the discussion of the actual presentation, and so this translation that I did is actually more complete than that one. So it wasn't a complete waste of time. So that's always nice to know.
Nice, that's great. It didn't have any of this discussion portion.
No, it's just the portions of the presentation at the beginning.
Where did you find it? Where is it?
I posted the book. The book, it's a collection called French Philosophy After 1945, which is kind of ironic given that this talk was actually presented in 1939. But let's see, where is it? Anyway, it's you have to scroll up a ways in the chat to find it. But I managed to get the interlibrary loan to do a scan of it for me, and I haven't sat down and compared the other translation with mine to see where there are divergences or alternate choices and so on, which I'm gonna have to do at some point. But at least it's not the other one. At least is not a complete translation like this one is. Okay. Thank you everyone for showing up and for your contributions. And we'll continue next week, and I think we should be able to finish the text next week, hopefully.